Cool. All right, so I got a few demos lined up. So if you are watching a video, just imagination for some of these, because I'll flash some stuff like this balloon here, this little purple balloon. And now if I rub this against my hair, you guys ever done this?
Yeah.
Right, it's gonna be like a charge transfer, right? Right, so you guys start talking about electrostatic charge here. Right, now, hair or animal fur tends to want to get rid of electrons, and latex wants to pick up electrons. So I should have a negatively charged balloon. If I get this to work. Oh, that is working pretty good. Right, yeah, like, okay, so it'll stick to a neutral wall, right? So stick right there, right? Right, now how about, work towards this, fix that real fast. Okay. How about, I got a couple of tapes taped together. I already taped these fast. This here. All right, so for anybody watching the video, I take two pieces of tape together. Okay? Now this whole thing is neutral, right? Probably similar number of protons and electrons. But I'm going to strip these two tapes apart really fast. When I do, there's going to be electron transfer. One of these picked up a little bit more electrons than the other one. Okay? Now, if I hold these together, should they attract or repel? Let's see, one's positive, one's negative. They should attract. Let's see. Oh, okay, so they do a little bit, right? A little bit of traction. So wearing out over the day. Yeah, you guys see some traction, right? Right. But I wonder which one's the positive one, which one's the negative one. Oh, well, I know this purple balloon over here is negatively charged. So put this one aside real fast. Pull this balloon. Let's see what this does. Ooh, kind of hard to tell. I think this is getting let me try to scan. Let me rip these apart one more time. Reset this thing. So take two here. Let's see there. Ooh, yeah, I think it's a little better. I see a little bit better traction. Okay, so set that one to the side. Okay, bring up balloon and oh yeah, that's a really strong attraction now. Show for the video. Okay. Definitely see an attraction there. Okay, if that's an attraction, then the other tape should probably do what to the balloon? Repel, probably. Let's see if it does. Oh yeah. Whoa. Oh yeah. That's a really strong repulsion right there. Okay, so I'm glad I reset that because now I get a really good demo. So I think it's showing up in the camera. There's definitely a repulsion right there from the balloon. Ooh. Okay, so some kind of electrostatic force. You know what, let me flip on this Van de Graaff on, just do a bunch of demos. And so I'm going to do a Van de Graaff. Tomorrow roll a video of Van de Graaff too. So should be good for a video. But here, let me show you guys what's inside this thing. Okay, so you guys see that blue latex belt right there? Got a blue belt. Okay. And see there, when it turns on, it's going to rotate. It's just going to barely brush up against this wire mesh right here. I said. Now, the latex, remember, is going to grab a bunch of electrons, which is going to leave this dome positively charged, right? Let's check this out. All right, here we go. All right, and then, oh, yeah, ooh, I can feel it already. It feels fuzzy. Now, if I touch that thing, do I want to touch that thing? I'll probably get a shock. How about this? See if you guys see a spark. It's been working on and off today. It doesn't work very well with humidity, but let's see if you guys see a spark. Ooh, you guys hear that? All right, I'm gonna let charge up again. We do so, maybe you guys might see it. Ooh. Ooh, yeah, you guys see that? Ooh. Now this thing, yeah, this thing will shock you if you touch it. Yeah, I will leave this back on that lab table the rest of the week, and then you guys want to shock yourselves sometime later. Yeah, that's a fun activity. Yeah. But today, do some notes. Do some notes here. All right. Let's go. Electrostatic force. Right, so you guys saw some attraction, some repulsion just from static charges, right? Tapes, the balloon. Take up my notes here. Hold on, don't want that one. Sorry, guys. Here we go. What is that force, and what variables and units are involved in this? This is right. So, say I have a couple of charged particles. Right? Yeah. Let's go for the picture first here. Let's say that this charged particle, and I'm going to label a charge Q. So Q sub 1 is, let's say it's like 3 microcoulombs. Okay. Okay. So Q is a charge. So Q is a static charge. Okay. That's going to be measured in coulombs. Okay. So some number of coulombs. Right. I'll give you guys a table of variables and units here in a minute too, but just start electrostatic charge. Okay. And notice I said microcoulombs. Ooh, what is micro again?
10 to the negative 6.
10 to the negative 6, right? Like million. Okay, so it's like millions of a coulomb, right? Let's say there's another static charge here. I'll do Q2 equals, let's call it positive 5 microcoulombs, right? Oh, so opposite charge, or no, whoops, no, I didn't say charge, plus and plus. Okay, so if I do plus and plus, is that going to be repulsion or attraction? Oh, you're repulsion, right? Because same charge, right? So I wonder what this force is. F. Right? Oh, is it the same force on both of them? Same force? Newton's third law. For every force, there's equal and opposite reactive force. Anytime two objects interact, it has to be equal magnitude, right? Opposite direction. But do you think the distance between these two also matters? The distance. Okay. Just gotta make up a number. Let's call this like distance equals 7 centimeters. Okay. So say I have 3 millionths of a coulomb here, 5 millionths of a coulomb here, separated by a few centimeters. I wonder what that force is. So here's the structure of the formula. It goes force equals K, Q, Q, so Q1, Q2, all over the distance squared. Okay. Now, hopefully the structure of that formula looks really familiar. What does that look a lot like from last semester?
Gravitation.
Universal gravitation, exactly. Guys, remember it was 2 masses multiplied together, also divided by the distance squared, right? Right? Okay, so there's also the inverse square relationship between force and distance, just like it was for universal gravitation. Right? Instead of 2 masses, now it's 2 point charges, right? Instead of kilograms, it's coulombs. Okay? I see one difference could be electrostatic force might repel or attract versus gravity only attracted. But here's another difference. See that K right there? Now this is going to be constant. Now, last semester was capital G, right? G-M-M over R squared, right? So what is that K? That K is 9.0 times 10 to the power of 9 Newton meters squared per coulomb squared, right? 10 to the 9, that's like a billion, right? Ooh, do you guys remember universal gravity constant that fit in about this slot was like 6.67 times 10 to the negative 11 in a bunch of units? 10 to the negative 11 versus 10 to the positive 9. Whoa, aren't these numbers, these constants, isn't this different from universal gravity constant by like 10 to the 20, right? Negative 11 to positive 9, that's 10 to the power of 20. Yikes. Okay. Which force do you think is considered to be the much stronger force? Electrostatic or gravity? Gravity, right? Now, it is mixing apples and oranges a little bit because, you know, it's like different units, but yeah, I mean, 10 to the 9 compared to 10 to the minus 11, yeah, much stronger force. Here, even like this, right? So what force is going to pull this pen down? That's gravity. But what brings it to an abrupt stop? Well, see, there's some normal force, right? Some surface force between surface of paper and the pen. And on the atomic scale, it's like a bunch of atoms. So you got positive nucleus, negative charge electron field. So you got a bunch of electrons here, a bunch of electrons here that are electrostatic force will easily beat gravity, right? And so let's do a calculation because I threw some numbers in here. So let's pop them in. So what is this force equal to? I got 9 times 10 to the 9 Newton meters squared per coulomb squared. Okay. Let's see, there's 3 microcoulombs, so 3 times 10 to the negative 6 coulombs. I've got 5 times 10 to the negative 6 coulombs. And then all divided by, okay, 7 centimeters. Isn't that like 7 times 10 to the what?
-2.
-2. Good call. Meter. And then don't forget to square it. Okay. Huh. I wonder what the magnitude of that force is going to be. So just make up some numbers on the fly. See what happens. So 9 times 10 to the 9. So 3 times 10 to the -6. So like millionths of a coulomb. 5 times 10 to the -6. So yeah, millionths of a coulomb. All divided by 7 times 10 to the -2 quantity squared. Okay. She said centimeters separation. Wonder how many newtons this is going to be. 27.6 newtons of force. Whoa. You guys remember your largest lab weight, mass of a kilogram, has a gravitational weight of almost 10 newtons, like 9.8, 10 newtons. Okay? This is like 2.5 or 3 of these. This is almost 3 of these. And we're talking about like 2 little like millionths of a coulomb charge separated by a few centimeters. Yeah, talking about like almost 3 of these worth of force. Okay? So that is a pretty big force right there. Let's do. Hey, how about let's get to flowing electricity, because at some point you have to bring in the batteries and have some kind of like current flowing. So give you guys a table of variables here. Let's do this. We'll do variable and unit. Okay. I'm going to give you guys 5. So 5 variables in the corresponding units. Okay. So when you see Q, it might be a capital Q, it might be a lowercase q. We're talking about a point charge. Okay. And that's going to be measured in coulombs. So capital C. Okay. If you see, now what if that charge is not static? What if it actually is flowing at some rate? Okay. Well, that is what current is. And current, we're going to do capital I for electric current. And that is measured in, I bet a lot of you guys know all these answers even before I write them. What is current measured in? Yeah, amps. Yeah, amps. Okay. So full name is amperes, but yeah, a lot of times you just say amps. Okay. And 1 amp is the same thing as 1 coulomb per second. Okay. Now, you guys remember there are like 7 things you can fundamentally measure? Me, if I were to design that table, I probably would have called coulombs like one of those things, like mass or displacement or time. But almost all textbooks consider amps to be like fundamental thing you can measure this electric current. So a lot of times 1 coulomb is actually defined as 1 amp second. So amp times second. So I don't know, I think it's a little weird, but that's what most books do anyway. Okay. Now, why would current flow? Like what causes electrons to move? And okay. So you need some potential difference, and that could be capital V or Greek letter epsilon. You call that potential difference, which is also called voltage. Okay. So you have a potential difference or a voltage. And the unit for that, you guys might take a wild guess what the unit is. Well, volt. Yeah, volt. Okay. Now, what is 1 volt? 1 volt is equal to, okay. This I have not memorized. I had to look this up myself this morning. 1 kilogram meter squared per amp second cubed. So there you go, I guess, if you want to tie it back to other units, that's how it relates. Here. You guys ever look on a battery? Do you guys know, like this AA battery right here? You guys know how many volts this is? Right? If I pop this in an appliance, here's sort of how this works. Think of this battery kind of like a pump. I'm going to give you guys an analogy here in a few minutes too. Think of like kind of like a pump, like trying to pump electricity through a circuit, right? So I pop this in, say like a flashlight, for example, and that will induce a current to flow. Right? The more voltage, maybe the more current that flows, right? Sort of makes sense. How many volts is this guy, right? Do you guys see 1.5 volts? You guys see that 1.5 volts? Okay. see if you guys can possibly see that at home. I don't know if it's blurry or not, but it says 1.5 volts right there. That's also true for AAA batteries, C batteries, D batteries, any of these cylindrical type batteries. They're all 1.5 volts. I bet a lot of you guys know what this boxy battery is. How many volts is this guy? 9. Good call. That's 9 volts right there. Guess that. Then you guys at home, that's like 9 volts. Yeah. Ooh, that's like 6 of these. At least in series. So if I took 6 of these and stack them like in a row, like one after another, like this, yeah, that'd be like having one of these worth of voltage, like trying to pump electricity. Okay. Now, how many guys have ever taken a wire and directly touched the positive to negative lead of the battery? You guys ever done that? Right? Yeah. If you have, what happens to the wire? It gets very what? Very hot, very quickly, doesn't it? Okay. Because that is actually called a short circuit. Because the wire itself, made of metal, really good at conducting electricity, itself has almost no resistance. And that's the next one. Get it right here. Capital R for resistance. Okay. And the unit is called ohms. And the character for that is Greek letter omega. Okay. So volts could be capital V. Oh, you know what? I almost forgot to mention that too. Volts, I think this is the only time this entire class where I use the same character for both the variable and the unit, right? Capital V for both. Right? Again, a lot of textbooks like to use the epsilon for potential difference or voltage. I just always use capital V for both, but one thing to keep in mind, right? Because it's not like distance is in meters or like current is in amps or right, resistance is in ohms, right? So use capital V for both these. It's just something that we've done. So let's keep doing that. So what is 1 ohm? So 1 ohm is equal to 1 kilogram meter squared per amp squared second cubed. That's how it relates. Okay. So yeah, if you attach the positive end lead directly to the negative lead, say with the wire, right? Not quite well. Yeah, right. This would heat it really fast, and then it would drain the battery really fast because this wire has almost no resistance. Okay, so maybe that sort of implies that anything else that you normally actually do plug a battery into probably has some associated resistance, right? Okay. I'm going to throw in one more variable and then give you guys some formulas and an analogy to tie all these variables together. Okay. And the last one is capital P, power. Okay. And this one you guys already know from last semester. What is power measured in? Yeah, work over time. So it's like joules per second, right? Which is also called watts, right? Capital W, watts, right? Where, okay, you guys remember this one. 1 watt is the same thing as 1 joule per second. And then you can break that down further. Do meter per second if you like that. Kilogram meter squared per second cubed in base SI units. Okay, so there you go. Okay. Now, how do all these variables relate to each other? Well, how about this? Do you guys think if you go from this 1.5 volt battery to this 9 volt battery, have like 6 times the voltage? Let's say hook up like some appliance. Do you think you would get like 6 times the current that results from that? Right? So there's probably a direct proportion between this voltage and this current. Right? And if I remember if there was no resistance, like just that wire, then the current flows too fast. So probably the more resistance you have for like some given battery, right, do you think the less current, like these two might have an inverse relationship? Okay, so let's see, I need a direct relationship between these two and an inverse relationship between these two. Okay, so put that all together and you get something called Ohm's law. Oops, this Ohm's law. Yes. So that goes, the current that flows is equal to a voltage acting on a resistance. So you have some battery, you pop into an appliance, to a circuit, flows voltage, measured in volts. You can also call it potential difference. And then that appliance will have some associated resistance measured in ohms. Okay? And as a result, there's going to be some current that flows in some amps that you can quantify. Right? A lot of times Ohm's law is written in a non-fraction form as V equals I R. Right? So if you ever see that, but you guys do see it, these are the same thing, right? You guys see that? Right? Now I prefer the fraction version myself because I think it's better explanation for cause and effect, right? Put a battery on some circuit, it causes some current flow, right? So something like that. There you go, either way. Now, another question I might ask is, well, how fast is this battery being drained? Like if it has some finite amount of energy stored in chemical bonds, okay, and you plug into some appliance, it's going to last like 20 days, 30 days, 40 days. Like how long is this thing going to run? So let's bring in power. So capital P, well, you guys remember that stands for power, measured in watts. Okay. Give you guys three perspectives on this. It could be current times voltage, like P equals IV. That's pretty good looking one, right? Okay. So if you know the current, you know the voltage multiplied together. Okay. Or it could be, if you take Ohm's law right here and substitute out the voltage, you can get current squared times resistance. Right? Or if you substitute out the current, so go the other way, you could get voltage squared divided by resistance. So those are three different perspectives on the same thing. Right? What rate is the energy going through your appliance? Okay? Let's do a quick example. You guys ever seen a light bulb that maybe says like 40 watts, like 40-watt light bulb? Okay. Now, 40-watt light bulb, actually what's going on is it has some filament or like, so there's some associated resistance. Okay? And it's assumed that, okay, you're going to buy this in like some country that has some electric grid that has some known voltage on it. Now, if you say buy this bulb in the States, then you might know that, okay, well, probably designed for 120 volts and, and there's your power, like 40 watts. Hey, I wonder what the actual resistance of, say, the filament in the bulb would be. Okay? I think I just played you guys a video of the bulb, right? Like flashing. Okay, so a light bulb is actually going to be my classic example of a resistor. Okay, let's check this out. Like each of these three formulas, what I was going to say is might be useful or more applicable in some certain scenario. Or if you're trying to figure out, like, oh, if I change this variable, how does that change something else? Sometimes one of these is like a better framework to think in terms of. So we can figure out the resistance of this bulb by applying this very last formula. So the power would be 40 watts. We get that. We divide down the V squared. So if you know, you hook that up to 120 volts squared, you know, if you plug it into the wall, right? Okay. That's 1 over R. So then I take the reciprocal of that. 360. So this bulb would have a resistance of probably 360 ohms. Okay. Maybe they could actually advertise it that way, but then wait, what? So, but maybe watts is easier because okay, more watts, it's gonna be brighter. So, right? Okay. Guys get that? Okay. Now, when I was first learning all this electricity stuff back in high school myself, it took me a couple of weeks before all this stuff clicked because all these variables that we're talking about are, well, they are invisible, right? Hard to really see what's going on, like volts, current, volts, voltage and volts, or current and amps. So eventually, though, I learned a particular analogy that I'll show you guys right now. And then this is where this clicked in, made sense for me. And so electricity flowing through a wire, kind of like water flowing through a pipe. Draw a pipe system here. A little crimp in this pipe. Ooh, that's that. Okay. So something flowing through this system, right? So set up a table here. That's this analogy. So electricity through a wire. You can think of sort of like water through a pipe, right? Then what parts would be analogous to what? So voltage, okay. Think of that kind of like pressure. Okay? And if that's true, then your battery is kind of like a pump, right? Like trying to push electricity like through some circuit. Okay? So this might be volts, this might be like pascals, that's for you. Current, like the rate that electricity is flowing through, like coulombs per second, like amps. Okay? Think of that kind of like the flow rate of the water, like gallons per minute, right? Gallons per minute. There's some gallons per minute going through here, right? Okay. And I might say these two are directly proportional to each other, right? I mean, that's what Ohm's law says, right? So Ohm's law says either I equals V over R or V equals IR, right? So connect the story back to that formula, right? So if you double the pressure, then that should probably double the flow rate. Kind of makes sense. And one last thing, resistance to complete Ohm's law. Right? So some number of ohms. Now this one's a little bit more abstract. Think of it as the reciprocal of the cross sectional area. Okay. That's what this crimp in the pipe is about. Okay. This crimp in the pipe is kind of like a resistor, kind of like a light bulb, right? Kind of like a volt. See, if you did not have that crimp in the pipe, then you put on a little pressure and the water just flows like crazy. Drains your battery really fast. That's called a short circuit. Okay? But if you throw in a resistor, could be a bulb, could be something, right? Like any appliance should have some amount of resistance in it. You can slow that down and actually calculate how much current flows through. Okay? Makes sense? Okay, so I'm gonna draw you guys a schematic and then break out a breadboard and a multimeter. So let's look at a schematic of this. Right, so what is going on here? Well, whenever you guys see two parallel lines, one longer than the other, this represents a voltage source. Okay. For example, a battery. Okay. Just pop in a battery there, right there. Okay. Maybe it's, I'm just gonna make up some numbers. Maybe, let's go with the 9-volt. Say like a 9-volt battery. It's close to like this boxy battery. Just plugging it right there. And the long line represents the positive terminal, and the short line represents the negative terminal, something like that. Although, if you don't know that, then it doesn't really make a difference. Like the math works out either way. But sort of technical. What do you guys think this jaggedy line over here represents? How about a resistor? Resistor, right? For example, a light bulb. Okay. Hey, if we got say a voltage source connected to this resistor, and then these connecting lines could represent the wire, or something like that, then I wonder how much current is flowing through, and then what's the power output, something like that. Oh, good. Well, I need to give you guys a resistance here. So again, I'm going to make up something. What this is like, I don't know, say 36 ohms, something like that, like 36 ohms. It's on the flat here. Okay. Also, this is called a closed circuit. You can put other things on this diagram too. Obviously, it's an extremely simple one. Right? But here, for example, maybe you have like a like a switch, right? Now, if you have it open like that, that could be called an open circuit, and then the electricity would not flow. And then you close the switch, and now the electricity can flow. So that's called a closed circuit again, closed circuit. And so, how much current is flowing through this thing? Well, I know I is equal to V over R. So then I would say there are 9 volts acting on 36 ohms. That would be like a quarter of an amp. Whoops. 0.25 is a quarter of an amp. And then I wonder what the power output is, like how many watts. So I gave you guys 3 formulas for that. This is one of those formulas. So I'm going to take the current, 0.25 amps.
Good afternoon, staff and students. Please disregard the interruption. For the tennis students today that were supposed to be released at 1:15, we are not releasing them. It has been canceled due to weather. So please do not release any tennis students at 1:15 today. Thank you.
Sorry. All right, so there you go. So you got a little over 2 watts. Okay, that's it. Any questions so far? Okay. All right, so let's take a look at this this here breadboard. So what's going on with this? I see lots of holes where you can plug things in. I've plugged in a little LED light here. You see that? Okay. Now you can create circuits with this circuit board, but you have to know what wires are going on behind the scenes. So I can tell you that basically lots of short rows of like 5 dots, like 5, 5, 5. Right? There's a wire connecting these 5, wire connecting these 5, wire connecting these 5. Okay, and then same story on the side. So these 5, these 5, these 5. Right? And then how about like where these red and blue lines are? There's a wire that runs along this whole and here, and then here. It's 1, 2, and then here and here. Okay, so now if you know like behind the scenes where the wires are running, then you can set up some circuits that make sense. I have, let's see, this multimeter. Now let's take a look at this multimeter. Let me measure on this. So this has this toggle switch. Could be it's a combination of voltmeter. There's an ammeter in here. Now everything to the top left, I see some voltages, right? Now there's a solid line and then a dash line that refers to some kind of DC. Versus you guys see this squiggle line over here that refers to alternating current. Okay. So if I switch it over here and then I take the leads of this multimeter and then say plug this into some alternating current source, then it should tell me like 120 volts, something like that. Now I'm not going to do that because I don't want to go plug in these leads directly into in these outlets because that would be dangerous. It might be like a fireball that blasts out of there. Seen that before. So what I will do though is I got an extension cord. Now this is hooked up to an outlet. So again, like I could jam these in here, and if everything went good, then we get a reading of 120 volts. And I'd love to show you guys, but I'm gonna avoid doing that. But instead, I have a cell phone charger. Now the cell phone charger, this adapter will step down the voltage from 120 volts all the way down to 5 volts, and it'll also change alternating current to DC direct current, right, which makes it a lot safer. You guys see it close up there? Actually, it'll take input anywhere from 100 to 240 volts, so that's the entire world standard, right? And then either 50 or 60 hertz, and it'll jump it down to only 5 volts DC. Same thing should be true for your laptop. There's probably like an adapter box on it so that you can plug in your laptop wherever. But if you have some appliance like I don't know, like a toaster or stereo or something, then not necessarily work outside North America. But plug this in here, okay. And then say got a couple of leads. Okay. Is it safe to touch each of these leads right now? Yeah, I don't even feel anything. I don't feel a shock or anything. Okay. But let's check this out. Should be 5 volts across this. Let's see if there's a 5. Actually, you know what? I can't quite do. I don't think it's gonna work, but let's see if it does. Oh, actually, no, that's good. I see 4.95 volts. That's it. 4.95 volts. So that's about 5 volts, isn't it? How about this breadboard circuit over here? Okay. So now, okay, I'm touching both leads of the LED. And I'm not getting anything. LEDs are polarized, so the electricity can only run one way. So if I switch these leads like this should light up. See if it does. It sure does. Look at that LED right there. Right? Also has some old Christmas lights cut up back there that I'll probably have you guys do a lab next week. But the Christmas lights are not polarized, so you can do either way with the light up. Just don't have one right here. Now, what I'd like to do, let's see real fast if I can do this, like jam these leads into this breadboard and then light it up that way. Now it's set. Oh, this might actually get to work. No, this one pop out. Okay, it's really hard to make these leads like jam into this breadboard because they're like, yeah, like they sprayed wire in. So, okay, but let me do my best, see if I can get a voltage rating across this anyway. So we're gonna prop this get this all together. Right. Yeah, do you guys see, well, kind of bouncing around, but 4.8, actually it says negative 4.8. Okay, whoops, negative 4.8. Is that? Okay, if I switch these two leads, then it should go back to positive again. There you go. Okay, so 4.86. You see 4.86. Okay. Now the way I'm connecting, let me go to my schematic here because it's kind of hard to see because I got a little tiny breadboard and got wires all over the place. So to use this, right, this is like my voltage source, like 2 leads. Okay, this is like my LED bulb, right, and I was connecting these 2 leads like this. So remember, for the voltage, it's measuring a potential difference. So it's like, there's like a high voltage and a low voltage. And that difference happened to be 5 volts for this particular bulb and this breadboard stuff, right? Now, I could measure other things with this multimeter. I can switch this toggle over to the one that says, well, amps, or it actually says milliamps. Let me zoom in. Right? You see milliamps and amps right there. Right? So it's probably close to like milliamps, like that order of magnitude. So I want that. Now, if I have you guys do some lab version of this, then you actually do have to take this this red one out and actually switch it to a different plugin, right, for just to measure the current. Right? And also, the way you measure the current is different than how you measure the voltage. Tomorrow I need to tell you guys about series versus parallel. To measure the voltage, I did a parallel setup where the electricity just flowed through the bulb, but I've got one lead here, one lead here to measure the potential difference. But you can't measure current that way. Current, what you have to do is actually break open your circuit and have the electricity physically flow through the multimeter, through the ammeter, when it's on this toggle switch and when this red is plugged into, like this left bulb here. Okay? So, yeah, I would try this, but yeah, having trouble like things to plug this breadboard. Yeah, so different ways you have to use this multimeter to measure either voltage or current. Okay. Can give you guys a real fast crash course today, but yeah, next few days try to see more of those too. Let's see. I think I covered everything I need to cover. Huh. We did that. Yeah. All right. I don't know how I went so fast with you guys, but you guys got any questions about anything so far? I guess so we can do is let's do a couple more examples. So what do you think? Okay, let's do a voltage source of like 9 volts again. So we got like a 9 volt. Okay. What if I had 2 resistors? Let's call this guy like 3 ohms, and call this guy 6 ohms. Right. So, notice those resistors like one after another. Like if you trace around, like you'd have to go completely through one resistor and then through the other one sequentially, like one after the other. Okay. So that is called, these 2 resistors are in series with each other. So in series. I was going to save this for tomorrow, but let's go flash forward today. Preview. Right. So what do you think the total resistance is from the point of view of this voltage source? Do you think it's just 9 ohms, right? 3 plus 6? Right. It sure is. So in series, you can say the total resistance, you just add them together, R1 plus R2. Right. So that's going to give you 3 ohms plus 6 ohms. That's equal to 9 ohms. Okay. And then if you do the rest of the math on it, so let's go over to Ohm's law. So the current that flows through, voltage on resistance, we've got 9 volt voltage source acting on 9 ohms of resistance. Wouldn't that be like 1 amp? So like 1 amp of current. Okay. And then if you want to figure out what is the power output in watts, let's do P equals IV. So I got 1 amp and 9 volts potential difference. So that would be like 9 watts. Okay. Guess that. Okay. How about this though? What if I had the same 2 resistors, but I just hooked them up differently? Okay. So let's go same source, like 9 volts. But now I'm going to do something a little funny. Let's put 3 ohms right here and 6 ohms right here. Okay. Do you think the total resistance would still be 9 ohms? So it would not be. This is called in parallel. See, it's sort of like rungs of a ladder. Like I could tag on like more and more resistors. It would look like a long chain, like a long ladder. Okay. And before I give you the math on those, again, I'm sure there's a couple of guys out here actually that know how to solve these. want you guys to think about the mechanics of like, should this actually even increase resistance or actually would it decrease it? Right? Here's what I'm thinking. So there's resistance, obviously that's going to like slow down the electricity, right? So like decrease the current. So like the more resistance, the less like the more resistance, the less current, right? The more R, the less I, just inverse relationship. Okay. Let me give you guys a traffic analogy. Sometimes a traffic analogy is useful for currents too. Okay? What if this is like 3 stop signs? This is like 6 stop signs. Okay. Well, if they're all in series, like in a row, then you have to go through all 9 stop signs. So the total resistance is like 9 ohms. Okay, guess that? But if you have these resistors now in parallel with each other, got 3 stop signs here, 6 stop signs here. What if my voltage source is like a parking garage, right? So you drive your car out of the parking garage, you're driving around, right? You want to make it back to the parking garage at the end of the day because we got like closed circuit, right? Well, you don't have to go through all 9 stop signs, right? I mean, you hit this junction and you look to the right, and you look to the left, you see different numbers, right? Huh? Which path would you be more likely to take? What do you guys think? Yeah, probably just the 3 ohms, like the 3 stop signs, right? Because there's like half the number of stop signs, like half the resistance, right? This right here would be called the path of least resistance. You guys ever heard that electricity wants to follow the path of least resistance? Okay? So, I mean, if it's 1 car, then 1 car is going to go there. Now, what if you have like 100 cars? Right? You have like 100 cars. Now, if all 100 cars are saying, "Ooh, I like 3 stop signs rather than 6," after a while, you guys think that maybe the 6 stop signs is probably starting to look pretty enticing because hey, there's like no traffic over there. Right? So the end result is that there's going to be some proportional split, and most cars are going to go along 3 stop signs, but yeah, some cars are also going to go along 6 stop signs, right? Overall, the traffic. Where do you think the traffic would flow faster? In series or in parallel? Parallel, yeah. More cars are going to get back to the parking garage faster. Okay. So here, I'll go ahead and give away what is gonna wait for tomorrow. The total resistance in parallel. Here is well, there's 2 takes on this. Okay. So 1 over the total resistance is 1 over the first guy plus 1 over the second guy. Or if you know math or if you know this ahead of time, you might say this. You might just jump to this. You can do product over sum, R1, R2 divided by R1 plus R2. Okay. So this line and this line are the same thing. Let's do a calculation real fast. So this would be 3 times 6 over 3 plus 6, which is 18 on 9. That's 2 ohms. That's only 2 ohms of resistance. Do you guys see that the total resistance is actually less than either of the resistors alone? Right? Because say you start with a 3 ohm resistor and then you open up a new road, the overall resistance has to go down. Right? Is it? Let's finish off Ohm's law. The current that flows is, so V over R. We're looking at 9 volts now acting on only 2 ohms of total resistance. And that gives you 4.5 amps. Okay, 4.5 amps when they're in parallel versus back a few minutes ago when they were in series, it was only 1 amp. Notice the current actually went up. But that's exactly what you guys said should happen. But we're a little bit different. Okay. All right, so yeah, that's good. Pause point today. Before I got some Paul Hewitt signed up, you guys can see a little bit different perspective and then continue on this electricity journey.